So my subject is this, a priori components of science, Lavoisier and the law of conservation of mass. I mostly read things so that I can finish on time. In his book, Identité et réalité, Émile Meyerson argued for a philosophical a priori background in the case of all scientific conservation laws. My contribution discusses one of the specific cases he addressed, the conservation of mass in chemical reactions. And this is a historical case study exhibiting the influence of philosophical ideas on science. And it's a counterexample to the naive empiricist view of science, which is widespread among scientists, teachers, and students, and which should be corrected. The stereotyped view of a chemist shows him, her in a laboratory, always doing experiments. The view has been common since the time of the alchemists, also always in the laboratory, and there is a specific symbol, the balance. After Lavoisier, the balance became a symbol of chemists, as beforehand it had been that of apothecaries, and also of justice. It's usually thought that the systematic use of the balance transformed chemistry into an exact science. Earlier, the balance was a symbol of justice, represented by the Roman goddess Justitia, and it's a highly symbolical figure. She's a maiden representing purity. The scales represented the objective weighing of evidence in the case of justice. The sword represented power, authority, and blindfold representing impartiality. Not always, of course. The use of the balance by the chemist is supposed to imply that his or her conclusions are objective, true, impartial. Unlike the philosopher, a chemist is never shown reading or thinking. As a matter of fact, however, chemistry, as any other science, is a messy combination of thought and experiments. I think this image is very messy. That's what I want to show. Neither alchemy nor chemistry are purely empirical studies. Philosophy is a relevant component of both. However, it's not enough to tell that this combination exists. It's necessary to show it by specific instances. It's useful to undermine the empiricist view of science that is still a very strong influence in the thought of scientists, teachers, and students. I present today a simplified account of my paper, which was too big to present. I'll begin with the conclusions, so that if I must cut something, the conclusions have already been presented. Then the popular version of the proof or discovery of the principle, then some history, not legend, of the principle, Meyerson's analysis, and teaching issues. So, my main conclusions. The principle of mass conservation was neither demonstrated nor discovered by Lavoisier or anyone else by experiments. It was widely used without proof by Lavoisier and other researchers. Lavoisier and some other researchers thought that it was an evident, purely rational a priori law. It's not an a posteriori empirical law discovered or proved by experiment. It's also not an a priori purely rational law. It's a special application of the philosophical principle of causality in the sense of Émile Meyerson, the principle of identity or principle of permanence of substances. The structure of the principle of mass conservation, as that of any other conservation principle, is a priori the structure. Its specific scientific content, which may be tested, is a posteriori. Therefore, its epistemological status is mixed. It's not evident, it's only plausible. This is the nomenclature used by Meyerson. First, now the popular version of the experimental proof of the principle states that Lavoisier proved the principle. Most scientists, teachers, and students think that science is true and that all scientific laws are proved by experiments. They apply this to the specific principle of conservation of mass and retrodict that Lavoisier demonstrated it by experiments. If it's sometimes called Lavoisier's law, then Lavoisier, of course, proved the principle. Textbook, popular works, and the internet are full of descriptions, just like this one, which is from a textbook. Using precise balances, Lavoisier was able to demonstrate what other investigators had suspected. The quantity of matter does not change during a chemical reaction. This is the law of conservation of mass. Or another instance, the first experiments that conclusively demonstrated mass conservation were conducted by Antoine Lavoisier, a French chemist just before the French Revolution. Lavoisier provided the first quantitative proof of the important mass conservation principle. Another textbook. However, everyone who has studied a little bit of philosophy knows that it's impossible to prove any general law by experiments or observations. Even if you observe 1 million white swans, this does not prove that all swans are white. Of course, you may find a black swan. So neither Lavoisier nor any other person could prove the principle by experiments as a general law. The second popular version of the experimental discovery of the principle is weaker. Philosophers admit that experiments may lead to a discovery, although they cannot prove a law, the context of discovery, of course. Hence, it's more acceptable that Lavoisier discovered the principle of conservation of mass by experiments. Perhaps that's the reason why it's called Lavoisier's principle sometimes. Textbooks, popular works, the internet, and even philosophical works are full of descriptions such as this one. Lavoisier experimentally discovered around 1785 the law of conservation of mass. The author is a philosopher of science. Or by carefully measuring the weight of each substance, Lavoisier discovered that, so by experiment, that matter is neither created nor destroyed during a chemical reaction, a popular account. All historians of science who have made a detailed study of Lavoisier's work reached a different conclusion, however. This is Bernadette Pinson, a very nice historian of science who studied Lavoisier, of course. Lavoisier neither discovered nor proved the principle by experiment, he just made use of it in his experimental researches. This is a small quotation from a work by Bernadette Pinson, Lavoisier did not discover the law that bears his name after delicate measurements, but he applied it to experiments. Or another historian, Lavoisier did not find the law of conservation of weight as a result of experiments. He never performed an experiment to check the truth of this law. Of course, we should check historical accounts, having a look at the primary sources. Lavoisier's most clear presentation of the principle appeared only in 1789 in a chapter on fermentation of his famous Traité élémentaire de chimie. Before that, he had used the principle of conservation of mass implicitly since 1770. Let's see how it appears in the book. Quoting Lavoisier, it will be seen that in order to arrive at the solution of these two questions concerning fermentation, it was necessary first to be well acquainted with the analysis and the nature of the fermentable body and the products of fermentation. For nothing is created, neither in the operations of art nor in those of nature, and it may be advanced in principle that in every operation there is an equal quantity of matter before and after the operation, that the quality and quantity of the principles, he means elements, are the same, and that there are only changes, modifications. So this is the most clear presentation of the principle. And he continues. It's on this principle that the whole art of experimenting in chemistry is founded. Experiments are founded on the principle, not otherwise. One is compelled to assume it in all experiments, a true equality or equation between the principles or elements of the body which one examines and those which one extracts from it by analysis. One is compelled, and we should use it as a guide to experiments. In this chapter on fermentation, the fermentation experiments, he provides data of the experiments. The total weight of the substance was exactly 510, not exactly pounds. Livre is usually translated as a pound, but it was slightly different. We may think about pounds. Okay. Corresponding to about 250 kilograms. His numerical tables provide the weights with the accuracy of 1 grain, the French grain, that is about 53 milligrams. Okay, then for this total weight, this amounts to 2 parts in 10 million, right? This is one table showing the materials used in the experiment. Water, 400, I would say, pounds, sugar, 100, and yeast, which contained some water, but the dry yeast had this weight. And you see that figures are supposed to be exact to the grain. Those symbols mean 0, right, in his book. The best balance he could use was able to weigh up to 10 kilograms with a precision of half a grain, or 25 milligrams, about 2 parts in 1 million, right? But here, if we believe his figures, he could establish the weight with the precision of 1 grain and 2 parts in 10 millions. According to Lavoisier's data, the products of fermentation had exactly the same total weight. Not a single grain was lost or gained in the experiments. So he shows here the results, the products of fermentation, providing the weight of each component, oxygen, carbon, hydrogen, and so on, and the total weight is exactly the same as at the beginning. Indeed, his comment, as I have already pointed out at the beginning of this article, I may consider the substances submitted to fermentation and the result obtained after fermentation as an algebraic equation, and supposing successively each element of this equation as unknown, I can obtain from it a value and thus rectify experience by calculation and calculation by experience. Okay? That's Lavoisier. I have often taken advantage of this method to correct the first results of my experiments and to guide me concerning the precautions that should be taken for repeating them. But sometimes he didn't repeat them. Okay, he just corrected the results. Lavoisier used the principle in the analysis of his fermentation experiments to correct his measurements and to obtain an exact quantitative agreement. However, he did not obtain the agreement for each element of the substances. This is rather funny. He didn't have the trouble to balance everything in his reaction. So here are the materials used in the experience, and for instance, the amount of oxygen in water, the water he added, the water contained in yeast, sugar, and yeast. This is a total in hundreds of grain, right? If we transform this into kilograms, about 201 kilogram and something before fermentation. Results obtained from fermentation. You have here in his measurement units, and if we transform the total weight of oxygen after reaction is smaller, right? 1 part in 200, not 2 parts in 10 million. The weight difference was equivalent to 20,000 grains, 20,000 times the supposed precision of measurement. Lavoisier did not attempt to explain this difference. Lavoisier regarded the law of mass conservation as an evident or a priori principle, and not only he some other researchers also thought that the principle was evident, purely rational, a priori law, and this explains why he did not attempt to test it. You don't need to prove something that is evident. He used the same principle in other experiments before the publication of the book, as I had told. And these are some instances where we can see how he regarded this principle. So in his experiments of burning hydrogen and oxygen producing water, we could not ascertain the exact quantity of the two airs, two gases, with which we had thus made the combustion. But as it's no less true in physics than in geometry, that the whole is equal to its part. From the fact that we had obtained only pure water in this experiment without any other residue, we thought that we were justified, without any measurement, in concluding that the weight of this water was equal to that of the two airs which had served to form it. Right? Several textbooks present this experiment as one of the proofs of conservation of mass in chemical reactions. The mass of oxygen and hydrogen were the same as the mass of the water produced in the experiment. He just didn't measure the amounts of oxygen and hydrogen. But, of course, just as in mathematics, this should work. Another experiment, burning phosphorus in oxygen. This experiment gave results similar to those of the previous one, another thing. Its result was also that when phosphorus burned, it absorbed a little more than 1.5 its weight of oxygen. And I have obtained also the certainty that the weight of the new substance that was produced was equal to the sum of the weights of burned phosphorus and the oxygen that it had absorbed. And that was easy to predict a priori. In this case, it's not clear if he did get the weights independently, and if in this case he knew that the weights matched, but of course it was easy to predict. Another experiment on combustion of olive oil. Concerning the water which has been formed, it could neither be collected nor weighed. I have therefore determined it by calculation, always starting from the supposition that the weight of the materials is the same before and after the operation, which I regard as evident. Right? So, in no place does he say, as I found by experiment. No researcher before or after Lavoisier, up to the end of the 19th century, attempted to test the principle by experiments. The principle was used by several other researchers before Lavoisier. It was explicitly stated by some of them, and no one attempted to test the principle. Those historical conclusions, I cannot present the details here, they are in my paper. The principle was first submitted through experimental tests only towards the end of the 19th and beginning of the 20th centuries, so 100 years after Lavoisier, showing some apparent violations of the law. Tests of the principle of conservation were motivated by anomalies of the predictions of William Prout's hypothesis that all chemical elements are made up of hydrogen. This hypothesis entailed that the atomic weights of all the elements should be exact multiples of the atomic weight of hydrogen. This seemed correct in the beginning of the 19th century when Prout made his proposal. This is a table of the relative weights of the elements taken from Dalton. However, after 15 years, I think, Berzelius first and afterwards Stas obtained atomic weights that clearly did not obey Prout's hypothesis. They had fractions. Prout's hypothesis could be retained first if mass was not conserved in the formation of heavier atoms from hydrogen, or if ether or some other subatomic particles, anything, was emitted or absorbed in the synthesis of atoms as proposed, for instance, by Carl von Nägeli. Carl von Nägeli was not a chemist, he was a botanist, but he was influential in the discussion of the hypothesis. The famous chemist Hans Landolt made a series of careful tests of the principle of conservation of weight from 1890 to 1910 for 20 years up to the year of his death. His last paper on the subject was published posthumously. Landolt compared the weights of two vessels containing the reacting substances before and after the chemical reaction occurred in each of them. This is the kind of vessel he used. He put one substance here, the other substance here. The glass tubes was sealed. He weighed it very carefully, and afterwards he turned it upside down, so the reaction would occur through this tube. He waited for 2 days before making another measurement, so that the temperature had become again equal to the temperature of the room. There seemed to happen a reduction of weight of about 1 part in 800,000 of the weight of the chemical substances, or 1 part in 6 million of the weight of the whole devices. The observed changes were much larger than the largest errors of the balance. Landolt had taken all precautions. As he was very respected at that time, his results were widely discussed and his experiments were repeated. Some scientists confirmed the weight change, others could observe no change in the chemical reactions. To improve the experiments, he ordered the most precise balance that had ever been built. Some historians of chemistry say that up to now, no other mechanical balance can attain this precision. The largest errors were about 300 of milligrams, with mean deviations of 100 of a milligram, with a total load of 1 kilogram, precision of 1 part in 100 million. To ascertain the precision of the balance, he made about 2,000 measurements. The balance was operated from a distance to avoid any disturbance, for instance, the heat of the observer, or the gravitational attraction of the body of the observer, right? So there was a distance, and the balance here is shown without the thermal shield that was actually used in all experiments, and it was possible to make all the operation of the vessels at a distance without touching them. In the new series of experiments in 1906, Landolt only observed significant reductions of weight in the reduction of silver sulfate or nitrate by iron sulfate, this reaction. The mean change was a weight reduction of 0.29 milligrams for each 100 grams of silver. And remember that the precision was much better than this. Errors were at most 1/10 of this value. Meanwhile, the scientific situation had changed. The electron had been discovered. Special relativity had been developed. The ether hypothesis was not strong anymore. Why am I saying this? Because one of the suppositions was that in the building of complex atoms, there could be addition of ether, or ether could be released, and that could produce changes of weight. But if there is no ether, it's not a good explanation. Radioactivity had been carefully studied and understood, for instance, by Rutherford. Landolt became convinced that weight could not have changed in the reactions he studied. He looked for new systematic errors, and he found one, irreversible dilatation of the glass vessels due to heat and change of buoyancy. So there was an apparent change of weight because the volume had increased, so there was the effect of air upon the vessels. The experiment was not performed in a vacuum enclosure. This was unexpected because the changes of the temperature rise in the experiments were not so high, and he supposed that even if the glass increased in volume, then it would decrease to the initial volume after reaction. Landolt introduced new changes in his experiments, for instance, enclosing one vessel in another vessel with double walls. Even if this one would change its volume, the outer one would probably not change and things like that. He computed and applied corrections due to the irreversible dilatation of the glass vessels. Then the changes of weight became smaller than the balance errors. And he published a paper on this in 1908. His final conclusion, taking into account 48 experiments concerning 15 different chemical reactions, was that there was no weight change larger than the estimated experimental error of 0.03 milligrams for a total weight of 400 grams. If there was any real change of weight, it was smaller than 1 part in 10 million. That's his conclusion. Of course, even in this case, you know that he was careful enough to state that he could only speak about those chemical reactions he had studied, and to make an assessment of the result, taking into account the possible errors. So he did not state, I proved that mass is conserved in chemical reactions. The anomalies observed in the experimental tests of the principle were never interpreted as violations of the principle of conservation of matter. Landolt and the other researchers involved in the test in this period of the principle kept looking for systematic errors and for something that had entered or had left the system. Now I close with Meyerson's interpretation. In 1908, Émile Meyerson published the book Identité, réalité. There he studied the history and epistemological status of laws of conservation, including that of mass and some other subjects too. And after more than 1 century, I think that this remains the best historical and epistemological study of the laws of conservation. I'll describe just a few aspects of his analysis more in the paper. The principle of mass conservation was neither, he states, was neither demonstrated nor discovered by Lavoisier or anyone else by experiments. It was widely used without proof by Lavoisier and other researchers. Lavoisier and some other researchers thought that it was an evident, purely rational a priori law. It's all these Meyerson's conclusions. It's not an a posteriori empirical law discovered or proved by experiment. It's also not. Although Lavoisier thought that it was a priori, Meyerson says it's not a priori purely rational law, and he shows mistakes of many authors who had tried to derive the law by purely rational arguments, such as Immanuel Kant. It's, however, a special formulation of the philosophical principle of causality, or principle of identity, or principle of permanence of substances. And this principle states that something remains constant or identical in any phenomenon. The cause contains the essence of the effect, and vice versa. Any substance in the philosophical sense is conserved in phenomena. The structure of the principle of mass conservation, as that of any other conservation principle, is a priori, is the philosophical principle of constancy of substances. Its specific scientific content, which may be tested, you see, the principle of causality does not say weight or mass is conserved. Okay, it cannot say this. When we add this specification, then it can be tested. So its specific scientific content, which may be tested, is a posteriori. Scientists must find what remains constant. Therefore, its epistemological status is mixed. It seems evident when we think about its a priori philosophical basis. As a scientific law, it's not evident, it's only plausible. But we must check it. And finally, some teaching issues. The historical study and epistemological analysis of the law of conservation of mass provides a noteworthy instance of the influence of philosophical ideas in science. This is Lavoisier, and here are some books he read, he thought, right? It provides a nice case study that may be used in science teaching against the inductivist view of science. Lavoisier was strongly influenced by the philosophical principle of causality. In the paper, I show other instances of his thought that were also guided by the same principle of causality. And for that reason, he thought that the principle of mass conservation was evident and a priori. Other scientists thought that too. Lavoisier must, of course, be understood in the context of his laboratory and experiments, but that is only part of the history. It's impossible to fully understand him and other scientists without taking into account the philosophical dimension. Can we teach this uncommon view? Of course, there are difficulties. Resistance by scientists, teachers, and students to this kind of view, inadequate training of the teachers to convey this message, lack of adequate educational texts containing historical accounts that can be used to convey this message. And I have one specific suggestion. If historians of science would like to contribute to the diffusion of a new view of the history of science, it's not enough to publish papers in journals on history of science and things like that. We should introduce corrections in one of the most used internet resources, the Wikipedia, where the article on Lavoisier, for instance, is in English only, is viewed 450,000 times each year. Okay, more than 1,000 times a day. So, unfortunately, this source is full of mistakes. But it invites the contribution of people who are willing to correct and change it. So we could try to improve this, and this would have a strong impact. Historians of science have been summoned to do this 10 years ago by graduate students in history of science, who was working for the Wikipedia at that time. Now he's also working for the Wikipedia, and he published a short note in the newsletter of the History of Science Society. As far as I know, it didn't work. Why? Because you don't, you cannot claim credit for your contribution to Wikipedia. Your name will not appear there. You cannot add this as a reference to your curriculum. Okay? But let me again suggest that this should be made. I'd like to acknowledge the help from the Brazilian National Council for Scientific and Technological Development for supporting this research, and I'm also grateful to my research assistants who got very tired after this research. Thank you.
Okay, anyone have questions?
Thank you, Roberto. I would like to start with the almost the last, this one. You mentioned many mistakes in Wikipedia and even in Lavoisier verb page. And what kind of things?
But only the English article had 450,000 views in 1 year, more than 1,000 each day.
And the kind of mistakes you found there?
In my written paper, I showed that their version of the discovery of proof of the law of conservation of mass is there, as in many other places.
Just about NATO.
Hi, Professor. Thank you for the speech. There are some versions of Lavoisier's story that highlight his prior work as an accountant with collecting taxes and so on. And some of them give credit to this prior function as having something to do with his fixed idea on the conservation of masses and checks and balances and things like that. Do you think it would be still too narrow to give credit to this aspect of his backgrounds for the conservation of matter?
We can say that one thing was the cause of the other, because both appeared exactly in the same year. 1770 is the year when he became a member of the Ferme Générale, and he began doing those accounts of money, financial accounts, and usually money does not disappear or appear from nothing, unluckily, in the second case. And so everything that enters must go some way or remain. And I think the first historian who called attention to the similarity between these and his accounts of the balance of mass conservation was Partington. And afterwards, many historians of science have pointed out the similarity. But this is just, this shows that his thinking of that something should be conserved is being applied in two different fields at least. He also applied it in the conservation of heat. He also applied it also in his job as a member of the Ferme Générale, discussing how can you calculate what is produced in France. For instance, how much is produced in France concerning cotton, wheat, anything like that. And he said, what is produced is sold and consumed. So if you can see what is consumed, you can conclude what was produced. Law of conservation of goods. So this is a general way of thinking he used, and I think we cannot say that one of them has precedent upon the others, but that he embraced this law that something is conserved in many instances.
Thank you. That, very much enjoyed your presentation. Particularly liked how you highlighted texts for us to focus on. I have maybe this question might be a little strange, but let me try this. Lavoisier is often counted as one of the foremost Newtonians after the mid-18th century, and it strikes me as odd on your interpretation that on the one hand, he's holding on to a metaphysical commitment of sorts. He's presuming this conservation prior to the experiments, which is so very much anti-Newtonian.
Yeah.
This is a hypothesis that is being feigned. Newton said hypothesis non fingo. This is actually hypothesis fingo in a sense. Or we could follow Augustine here and say that maybe principle of conservation of mass is actually the best explanation. And there's an inference to that. And I'm curious how you would settle either one of these. And by the way, I kept on wondering, was the beer good that he produced? He used beer yeast.
Wine. Well, of course, the interpretation I follow is that presented by Émile Meyerson. I agree with him. And we can try to provide other interpretations. But I found that Émile Meyerson's interpretation is very strong when you look at the study he makes of several principles of conservation. He studies, for instance, the principle of inertia, and he shows how it appears a priori in Descartes' work, how it appeared in the Middle Ages, and so on. And of course, Newton did not attempt to prove it by experiment. After stating the principle, he presents 3 instances of the use of the principle, and none of them involves rectilinear motion. He speaks about how do you call this thing that turns the top, the motion of the planets around the sun, and the projectile are the 3 only instances he gives. They are not even examples of the principle. Lavoisier, several parts at the beginning of his treatise, he speaks about the importance of measuring everything, observing everything. You can't go beyond what you have observed and proved and so on. But we must look at his practice. The very first instance where he applies this principle was in his famous experiment testing whether water could be transformed into earth. He boiled water for some time into a closed glass vessel for a long time, and a solid residue appeared, and some people claimed that by boiling water, some part of the water had transformed into earth, and the crucial argument was weighing each part, weighing the glass vessel the water, the residue, and he expected that the residue had come from the glass, but the numbers did not match. But he said, it's close, show. But it didn't match. But he did never put into question the principle itself.
Roberto, first a comment to Pierre comment, a meta comment. Yeah, this hypothesis non-fingo. If you look to Newton's work on light, yeah, he makes a lot of hypotheses for before doing his experimental work, and the experimental work are clearly clearly ordered to prove the hypothesis. So, and in this, I wonder if it's a kind of period of conservation, because if you see the Benjamin Franklin's explanation to minus and plus electricity, it's also related. It is a conservation.
Yes.
And there are no experimental reasons for. You don't see the conservation, don't weight the electricity. So it's a kind of a priori use of the principle of conservation to explain the results of the Leyden jar.
Yes.
So I wonder if it's a zeitgeist of conservation. It's something related to the period, or it just the idea of conservation is always in science.
Thank you. Meyerson believes that the principle was always active, and he gives some instances from the 2nd century, for instance, a philosopher discussing what is the weight of smoke. And the citation he presents provides a very simple answer. You want to know the weight of the smoke, then you should weigh the wood, then weigh the ashes, and the smoke is the difference. That in the 2nd century. And he shows many instances that conservation ideas were used since antiquity. But I agree that in the 18th century you have a series of laws of conservation, and in the beginning of the 19th century too, the law of conservation, what we call law of conservation of energy too, and which was clearly stated by Meyer from the principle of causality. It's very clear in his first paper. And the law of conservation of charge was not discussed by Émile Meyerson. I don't know why. It would be a very good example to study. But once you think that something is a substance in the philosophical sense, it must be conserved, and you treat it as something real that cannot be destroyed. And so people thought about electric charges and other things like that in this way.
This is a sequel to a powerfully constructed presentation to demonstrate the principle of the a priori nature of Lavoisier's use of the principle of conservation of mass. What might we be allowed to say about Lavoisier and what he did? For example, might you accept the statement that Lavoisier demonstrated the importance of using a principle of conservation of mass, and demonstrate in the sense of to show, to make public, to make visible for people to see, not in any manner of logical proof, but simply like, look, it seems to work. So he demonstrated not the principle, but the importance of applying it. And I'm thinking in particular of that very early work that, from what I understand, originated from his analysis of the water quality of the canals and the rivers in Paris, where they would boil down the water and see how much sediment was remaining. And he was like, and suspected it was in fact coming from the glass and not from the water, and that by virtue of applying that principle, you began to say, oh, well, we have to like revise our ways of thinking about how we test the water and what the quality really is. In the same way, if you go through all those incredibly sophisticated instruments to weigh hydrogen and oxygen and combust it and come up with an amount of water that's even like approximately the same, you've kind of like made a very persuasive case, not a proof, and there's no sense that he would have done it without having assumed it to begin with, but that it shows like, yeah, you should really pay attention to the mass and that it's conserved. And I think the sequel of, imagining that mass is going to be conserved had a lot to do with understanding chemical composition and atomic matter and rearrangements of elements and stuff. So there's some level at which Lavoisier is doing something important about conservation of mass. How should we characterize it if it's not this way? And finally, I guess combined with that is, what do you consider to be, if anything, the importance of the precision of his instruments?
Thank you. I think we must always think that people are never the first to do something. In the case, Lavoisier was not the first one to use the principle and so on, but he used it often. His use impressed other scientists. It became usual to use the principle in general after Lavoisier. Not everyone agreed. Cavendish did not accept it. He criticized Lavoisier's opinion on conservation of mass. And yes, he had a large importance in the, I wouldn't say systematic use of the principle, because I pointed out exactly in the case of fermentation, numbers do not match, and he didn't discuss it. Information is there, and yeah, I don't have to discuss it. So it was not such a systematic use of the principle. Sometimes he just didn't bother to use it. So I think he did have strong influence in this sense. It's the same with the use of the balance. Sometimes people say, no, Lavoisier is the first who used. No. It was used by many people in many important experiments before Lavoisier and so on. He used it systematically, probably more than other previous scientists. This had an influence. So I think we can agree that he had a role in presenting something and calling the attention of other scientists to that something was important doing, but not much more than this, I think.
Professor Ana.
It's not a question, it's a short comment. But I heard once a colleague that included in his assessment, as part of the grade, his students had to either write a new article for Wikipedia or debug, correct the errors in an existing one. So that would be a way to get credit from the work apart from Wikipedia itself. So maybe we could all do something like that with our students.
Yes. The Wikipedia Foundation stimulates that in the United States and Canada. So there are many universities in both countries where professors prepare courses that have as an assignment to correct or even to add new articles to Wikipedia, and this has had a huge impact, not in the case of history of science. There are just very few cases of history of science courses in the United States, I think none in Canada, I think, that are doing this, 3 to be more exact, among hundreds of other fields. And unfortunately, I could find exactly the articles they changed, and the changes were not very good. Unfortunately. So there are some people trying to do this, but
So shame on the professors.
yeah.
Any other question?
I'm curious to know about more about the chemical application context of the various tests that were being done. You began with the story of Lavoisier and the fermentation, that was a context in which, chemical context in which he was studying, and then a silver compound was another example, and then with Landolt takes up the story later. Maybe there's some other people, and I'm curious, like which reactions, and whether there were classes of reactions that began to be chemical reactions that began to be analyzed in this way. Or I don't know anything about it, but I'm just curious.
Yes, I didn't address the subject of the reactions and how did those ideas, how were they discussed or accepted or not by other scientists. But the short story is what was the most important chemical contribution of Lavoisier? The study of the role of oxygen in chemical reactions that could explain things like the increase of metals when submitted to calcination, things like that, many other instances. His table of elements, which was not built alone, but with the collaboration of other chemists, and a chemical nomenclature that was much more clearer than anything that was proposed before. And we know that he discovered no single new chemical substance or chemical process except for one, that was the production of hydrogen from heating iron, that some historians say it was not invented by him, but by a colleague. So his main chemical contribution was the understanding of chemical reactions and the role of oxygen and things like that. And together with this, that was soon accepted by most chemists, people also accepted his more or less systematic use of the balance and more or less systematic of the principle of conservation of mass. It came all together. people are not discussing separately each of his contributions, but the whole contribution.
Okay, thank you, Roberto.